All right, so today the goal is to be able to describe motion actually in terms of the unit tangent and the unit normal. So last day I said, when you are moving through space, at every point there are two vectors. One of them is the vector in your tangent direction. Again, that's the direction you'd slide when you hit the banana peel. The other is the unit normal, which actually points towards the center of what? Anybody want to try that? The circle of curvature. And unless you're on a line, there is always a circle of curvature. Because if I'm bending to the left, then there's a big circle to the left. If I'm bending to the right, there's a big circle to the right. If I'm doing a really sharp turn, then there's a smaller circle because there's more curvature. So the normal vector points towards the center of that circle, and the tangent points in the direction you would slide. Now, we love vectors in this form. Life is good. When I give you a vector and say, oh, go in this direction, that's pencil and paper. But like we said, when you go outside, I don't think you're going to be able to find the z-axis, right, or the x and y axes. So when you go outside and I say, I want you to go in a particular direction, it's a heck of a lot easier if I said, okay, the tangent is pointing this way, the normal is pointing this way. I want you to go 10 of these and 3 of these. Okay, now I know exactly what I'm going to do. That's kind of like the vector stuff you did in trig. Do you remember in trig? This is how you did vectors in trig. The plane is going due north at 500 miles per hour. The wind is blowing due east at 50 miles per hour. So what is the plane actually doing? So you drew your one vector, you drew your other vector, and then you said, oh, that's what the plane's doing. You guys remember doing that? That was as easy as life could possibly be. What we're describing is literally that kind of easiness to say, I want you to go this much in this direction and this much in this direction and just simply add those two vectors together. You say, wow, that's not too bad. Because when I'm outside, that's the only way I can describe motion. I can't describe motion with vectors in this form with coordinates because I don't have an origin outside. I mean, I can set it up that way. So, when we do this problem, let's start from the beginning. Now, a lot of this is going to feel like review of last day because we kind of need it. Okay, so my r of t, just like before, x of t, y of t, z of t. All right, then I have my v of t, which of course is dx dt, dy dt, dz dt. Now, last day I did a problem where I gave you a vector with just t's in it. I gave you one that was fairly low level, you know, it's like 2t, 5, 6t, you know, something like that. And we found that the acceleration vector was the zero vector. You guys remember doing that? Now, why would I'm moving through space, why would the acceleration vector be the zero vector? I want you to think in simple terms. You're on the freeway. You're speeding up to pass a car. You're hitting your brakes to slow down. Now you're on open road. Maybe you put it in cruise control. You're just driving for a while. What's your acceleration? Numerically, 0. Why is your acceleration 0 if you're going 80 miles an hour? You're not speeding up or slowing down. When your speed is constant, your acceleration is 0. Okay, so in vector terms, if my velocity vector is a vector of constants, that means I am moving in one direction at a constant rate. I'm not accelerating. That's why the acceleration vector was the 0 vector. It's really important that we understand that. I'm moving, okay? I'm moving, but my acceleration is 0 in terms of numerical values of acceleration. So the example I use in Calc 1, when I'm first introducing this, I said, I'm gonna start at this end, I'm gonna run as fast as I can to the other side of the room, but then I'm gonna slow down before I crash into the wall. And then I'm gonna do the same thing in the other direction. Are there any times my speed is 0? Yeah, right? Hit the walls. Is there any time my acceleration is 0? Yeah, about the middle. When my speed is its fastest, my acceleration is actually 0. Think about that. Because I just sped up, I've reached my highest point, now I'm going to start slowing down. I'm going to have negative acceleration on this side, positive acceleration on this side, but right at that point it's going to be 0. When is my acceleration its greatest? When I stopped. My acceleration was greatest when I was changing directions. Now, does that kind of fly in the face of logic for a second? In this example where I'm running back and forth, my acceleration is greatest when my speed is 0, And my speed is greatest when my acceleration is 0. So when people hear a 0, they tend to think you're not moving. Now, if I'm just standing here, my speed is 0 and my acceleration is 0 because I'm not moving. But if I'm moving all over the place and I stop for a brief moment in time and I keep moving, my acceleration is definitely not 0. I might be changing direction. My acceleration is not 0 when I've stopped moving, unless I haven't been moving. Right? Does that make sense? Oh, okay. So try not to equate those things. So from a mental standpoint, when I'm moving around in space, a 0 vector for acceleration just simply means I'm going at a constant speed. That's an easy way to think about it. Okay? Now, last day we talked about, oh, this is a dying pen, hold on. I didn't reload very well today, I think. So we have our, we know this. Messy pen. Okay, we know this, and so as a result of this, we can also rewrite the velocity vector as magnitude of the speed times the unit tangent. I'll leave off the t's there for just a moment. And then we also know that we could write this as ds dt. Do I have ds dt right there in front of me somewhere in here? Can you tell me what is ds dt as a value? It's in right here, isn't it? This is what it is. This is what it always is. There's no exception. And this is also the magnitude of the velocity, isn't it? Oh, so this is the integrand when I'm trying to find arc length. And it's also, I know, the magnitude of the velocity. That's why we use these interchangeably. This, starting with this, right? You wouldn't say, well, let me find ds dt first. No, if I have the velocity vector, just find the magnitude of the velocity vector. I don't need to be clever. And now I have this, and then I rewrite it like this. But I want to take a derivative. Maybe I want to take the derivative of the velocity vector. This is too hard to look at and take a derivative of from a notation standpoint. It's easier to take the derivative in this form. So one of the reasons we write it in different forms is for the purposes of differentiation. But when actually I'm finding it, ds dt and the magnitude of v are exactly the same thing. You question or? Oh, okay. The hand looked like it was getting ready. All right. Now we did this last day. So if I differentiate this, then I have a of t. I'll write it like this, which is the derivative of this. And that is a function, and that's, so I still use product rule, but a vector stays a vector, and the other guy stays the other guy. Okay? So when I do this, what do I get? Okay, so I get, I'm going to write it, I know it's first times derivative of second, second times derivative of first. Okay? You with me on that one? So if I do this guy first, because I actually want the t first, just makes it easier. Then it would be ds dt, dt dt. Okay? That's just straight up product rule. I'm not doing anything different or clever. But what do we know about dt dt? What do we already know? Well, what is the unit normal? Isn't it 1 over the magnitude This was last day. This was a big deal last day. The derivative of the unit tangent is not a unit vector in general, but the derivative of the unit tangent is in the direction of the normal vector. We showed that last day. That was one of the more important conclusions we made, because we also showed that anytime you differentiate a unit vector, the result is orthogonal to the original vector. That's why we know this is in the direction of the normal, because it's orthogonal to the unit tangent in that rate of change. So all I got to do is make this a unit vector. Now again, this is not a unit vector generally. Now this is a unit vector, okay? So we did that, but I also recognize this. What is k again? What did we show last day? Isn't k this? Which I could also write as if I wanted to write it this way. Now, there may be an advantage to writing it this way because I already have a dsdt over there, don't I? Oh, so if that's the case, go back to here. What does that mean that the magnitude of dt is? Wouldn't it just be ds dt times curvature? Everybody see that? Just simple algebra right there. Huh. Well, that's interesting. So I got all of this stuff. So go back to here. That means that dt is equal to magnitude of this guy times the normal vector. Okay? But the magnitude of this guy is speed times curvature. So that means that I can write this now. I want you to see where everything came from because it's not complicated. Let's now swap out this for this, but swap out this for this because I want the n in there. So what does this leave me with? It would leave me with, I already had a ds dt, didn't I? So it's going to be ds dt times k times n. And that is the formula of the day, folks. This is the formula that describes all motion in 3 dimensions in terms of the unit tangent and the unit normal. And now why is that important? Because when we go outside, right, I need you to go that way this fast, right? Something to that effect, or that way this far. When we go outside, I need magnitudes and directions more than I need, coordinates, okay? So, if this is the standard way of writing things, I have just written acceleration as a linear combination of the unit tangent and the unit normal, and that's the key. So these things in front, think of these as constants. Because at any point in space, when I evaluate, now obviously they start off as functions, but if I said describe the acceleration after t equals 2, or after t equals 10, or after t equals 100, then these would just be constants, okay? What if I'm moving on a perfect circle? Tell me about this quantity, if I'm moving on a circle. We know this from last day. If I'm moving on a circle, then 0. Why? Because I'm not going in any straightness. What if I'm moving on a line? Then this quantity is 0, mostly because the curvature is 0. Oh, okay, so if I'm moving on a perfect circle, that means that all of my acceleration is directed towards the center of the circle. Remember we did that last week, the helix? If I'm moving on a perfect circle, 100% of my acceleration is aimed towards the center of the circle. There is no tangent direction. If I'm moving on a line, there is nothing in the direction of the circle. Everything's linear. So those are the extremes. It would be unusual for either one of these to be 0, but on a circle, one of them 0, on a line, the other one's 0. Okay, that makes sense. Now you said, but I'm not moving on a line, but I did a problem and it turned out I got a 0. How do I get a 0 if I'm not moving on a line? You can do everything right and get an answer that doesn't seem to fit. So let's keep it real simple. You're driving to Borrego Springs. Anybody ever driven to Borrego Springs? Incredible drive. And when you have a passenger and they're like, oh my God, check it out. Don't. Don't. Because when you go to check it out and that little guardrail that's like a 2-foot high little metal thing, and then it's a 1,000-foot drop into a beautiful valley, yeah, don't check it out. I've been in the car with the driver who wanted to look, and what happens? You come within a split second of, a really bad movie of flying off the cliff and, landing 1,000 feet below. No, the drive is incredible, but the driver can't look at the view. They have to keep their eyes on the road. So you're driving, and literally the road's doing this kind of stuff. Now, I'm always doing this, right? Constantly doing this. I'm on these curves all over the place. Am I ever going straight? Yeah. You're going straight a lot. Wait a minute, but it's like the windiest road ever. Well, if I'm turning hard to the left, and I stay hard to the left, won't I just go into a complete circle? If I turn it hard to the right, won't I just go into a complete circle? So when I went hard to the left and then I went hard to the right, maybe about right there, I am perfectly straight. For how long? Not very long, right? One brief instant in time. So from a Calc 1 description, that would be an inflection point. Oh, an inflection point is when I change concavity. So in this way, think about I'm changing from turning to the left to turning to the right or vice versa. Well, if I'm going hard left and eventually hard right, isn't there a brief moment that my steering wheel is exactly centered? That's when I'm going straight. Does that make sense? Oh, at that moment in time, I am not going in the normal direction. I am going perfectly straight. So right here, does that make sense? Right here, my curvature would be 0. The curvature is 0 at that moment that you straighten out the wheel. And it's only at that one moment in time. It's not a duration of time. So does that make sense? And hopefully it makes sense because when you're doing calculations, every now and then you're going to say, how in the world did I get that? That doesn't seem right. You're on the windy road, and that's where it was straight. Now, I've been on this turn for a really long time. Is it possible that my tangent could be 0? Because I've cranked it, and it's the way the road is constructed, I'm not adjusting it. I'm just holding it hard to one direction for maybe a couple seconds. Well, if I kept it, we agreed I'd go in a perfect circle. But for that brief moment in time, I am driving a circle, aren't I? For that brief moment in time, I am driving the arc of a circle, which means there would be nothing in the tangent direction for that brief time. So that's why it is possible. So we give these guys names. This quantity here, this quantity here. We call this A with a subscript of T, and we call this guy A with a subscript of N. Really clever naming. This is called the tangential component of acceleration. This is called the normal component of acceleration, and they are scalars. So my answer might be 3t plus 5n in the end, something like that. The tangential and normal components of acceleration are now defined to be forevermore Could I also call this magnitude of velocity squared? Could I call it that also? Sure, yeah. It just in this form, the way we derived it, we did it by differentiating that. But you can certainly call it, magnitude of v squared. Now, how are these guys related to each other? Well, this is kind of cool. This part you don't like. Because they both can be a lot of work to find. And we're going to do a bunch of examples where we find them. I am moving through space, and let's say this is AT times my tangent vector, and let's say this is AN times my normal vector. These are not unit vectors, these are multiples of 2 unit vectors. Yeah, if it helps you, just put numbers in. 7 of these and 5 of these, whatever you want. So that's the case. If that's the case, then my tangent vector ought to be about there, right? You all agree with that? Now, don't 2 vectors always uniquely determine a parallelogram? Don't we know that from early on? Except these don't uniquely determine a parallelogram. I can do a little better than that. These will uniquely determine what? More specific.
Rectangle.
A rectangle. Why? Because these vectors are at right angles. Is that a good thing? That's a great thing. Because that means I have a Pythagorean relationship here. Ah, what is the length of this? Wouldn't the length of this be the magnitude of A? That would be its length. So here's a really simple absolute. We love absolutes. AT squared, that's a scalar, remember, plus AN squared must equal that squared. There's a Pythagorean relation because I'm starting with two vectors that are at right angles. Now, why is that a good thing? Because that means if, by the way, of all of the things you're going to find, the magnitude of A would be the simplest thing. That would not be a complicated thing. I don't care how complicated your motion is. When you're taking derivatives, unless you have some really nasty product rules along the way, your derivatives were generally getting simpler, weren't they? They weren't getting more complicated. Now, I'm not talking the derivative of the unit tangent. I mean the derivative of the velocity vector. You just turned in a problem today where you had to do a velocity and acceleration. Did those derivatives get easier or harder as you went? They got easier. Yeah, that's usually the case. So finding the magnitude of the acceleration at a particular value is almost always going to be trivial. That's not a tricky thing. Finding AT and AN individually can be a lot of work. But I can use the Pythagorean relationship. Ooh. Now what I tend to do is I don't find AT and then use the Pythagorean relationship to find AN. I don't do that. You know why? Because if I made a mistake finding AT, then every single number I write in the problem is going to be 100% wrong. I actually do it differently. I find AT and AN, and then I see if they satisfy the Pythagorean relation. If they do, then I absolutely know they're both correct. The mistake a lot of us make is we find one thing and then we use a shortcut to find everything else, and that's fine if the one thing was right, but every now and then the one thing was wrong. Now it means everything we wrote was incorrect. And we could have checked it along the way, but we can't because we used the wrong number to get the next wrong number to get the next wrong number, and all hell breaks loose, dogs sleeping with cats, everything. Just, it's all, right? Yes, there's a Pythagorean relation, but use it as a check rather than a solve most of the time. Because mistakes will be made occasionally. So now, these are not hard to find. I already know dsdt, I already know k. This is kind of the oddball right here. So I have found the magnitude of the velocity, which is called ds dt. That's going to be a function of t. Its derivative is this guy. And sometimes that can be icky. More often than not, it's probably icky. It's probably not always easy. Excuse me. So I know that's the case, and we're gonna go ahead and do a problem and find these. So I'm going to piggyback again on something we did last day just to save ourselves some time, okay? Last day, we did a problem. Help me out. I think we did the one that we spent the whole class on with curvature. Help me. It was t squared, 2t, 3t squared. I want to use this one just because we've already got a lot of the results. It'll save us some time because we didn't do all of this. But all of this is located in the work we've already done to some degree. So then my velocity vector, 2t, 6t, and I'll go ahead and write the acceleration now. 2, 0, 6. The magnitude of my velocity was, what was it? We did 4, was it 2 times, I don't remember, 10t squared plus 1, was that what it was? Does that look right? I couldn't do this in my head. 4t squared, so 40t squared plus 4, yeah. So with that, this is also ds dt. So let's find d squared s dt squared. See, this is where we would find it. We would differentiate that thing. Now, is the derivative of that horrific and difficult and evil, or is that kind of low-level Calc 1 stuff? Yeah, that's not terrible. There's no product rule going on. Little chain rule maybe. So if I think of this as being raised to the 1/2 power, then this is going to be 2 times 1/2 10t squared plus 1 to the negative 1/2 times the derivative of the inside. So when all is said and done, I think we're going to get 20t over the square root of 10t squared plus 1. Not the worst thing ever. That wasn't that bad. Where does this go? Right here. Okay? Now, we have not, let me erase some of this. All right, so our tangent vector, right? 1 over this times this We got t over the root. We got 1 over the root. And we got 3t over the root, I believe. We did this right. And remember, I said the easy way to check this, because all your denominators are the same, is square your numerators and add them up. And hopefully you get 10t squared plus 1. If you do, then you know it's a unit vector still. I didn't lose that somehow or another. Okay? So right now, the first part of my acceleration, which I've erased here, is this quantity times this vector. But generally speaking, like I said before, we're going to evaluate this at a number, so you're not going to write it in function form. Okay? So you'd say, well, I can distribute this and do all that. No, I don't want to do that because I want to leave the unit tangent untouched. I want to use it and leave it intact. So I want my answer to be some scalar multiple of the unit tangent. I don't want to multiply that number in because then I won't be able to see what the unit tangent is. But we'll see what that looks like in a moment. Now, I've already got the dsdt. That's right here. Did we find curvature last day for this problem? Yes, we did. Let's save some time. For this problem here, what was the curvature? In function form. It was something truly diabolical, I believe, right? I think we had this on the bottom, I think it was squared, and we had a root on top of
100t squared
plus 10. Okay. Remember, we're evaluating this as a scalar. Is that correct?
But is it 2 on the denominator?
I just don't want that 2. I don't know why. It just bugs me. I left it out last class too, every time. Okay, we found this. We're saving ourselves some time. And did we find the normal vector at some point? Did we find the unit normal? I believe we did. What was the unit normal? Were the denominators of the unit normal these, or was it something else?
It was 100t squared plus 10.
That was the denominators?
Yeah.
Okay, so the 100t squared plus 10 under the root. I can't believe I actually remember this much. I can't remember what I had for lunch yesterday. That's not a joke. All right, what were my numerators?
1, negative 10t, and 3.
And again, two things again. Sum the squares, and I would get 100t squared plus 10, that's good. And always do the dot product of t. Always do both of those things to ensure two things. Ensure they're unit vectors, ensure they're orthogonal. It's extremely unlikely you have an error if both of those things checked. Okay? So now, my final answer, you could say, well, my final answer is going to be this nasty quantity times this vector plus the square of this quantity times... No. Now we're going to evaluate it at a number because that's usually what's going on. So I would like you to describe the acceleration in terms of the unit tangent and unit normal at some value. So let's just pick an arbitrary value. I think we used 2 last day. Okay, let's use 2. So what we want to do is find a of 2 in terms of t and n. And I want to show you how it looks because a lot of times we do extra work. Okay? When I'm out in space and I have a direction, and once I understand where that direction is, and then I have another direction, now taking scalar multiples of those directions is an actual easy way to describe things. So, at 2, let's calculate our coefficients at 2. So what is d squared s dt squared? So in other words, what is, I'll put it this way, at t equals 2, AT. By the way, it would be correct to say AT of 2 if you want to say it that way. You could say at t equal 2 AT is, or you can say AT of 2 is. It's the same thing, right? And what am I going to do? We'll put a 2 in for t, and what does that give me?
Root 41.
But what's the quotient?
Oh. 40 over root 41.
40 over root 41. Probably something ugly. And a n evaluated at 2 is, now a n is a little bit more work because what do I got to do? I got to put it in here, square it, and put it in here. But it turns out it's probably not going to be all that bad, because when I square this, won't it cancel with one of these? Did everybody see that? So let's put a 2 in here. So what is, we'll do it off to the side, because there's a lot going on there. So what is ds dt evaluated at t equal 2, or you can say it's the magnitude of v of 2. Both of these, you're saying the same thing. This would be the proper notation, or just say it like that. So put a 2 in there, and what do you get? 2 root 41? What is curvature evaluated at 2? I think we did this one yesterday also. So it was root 410 over
3362. 3362.
Pull down your mask a little bit. I'm sorry.
3362.
3062?
33.
3360. Sorry. Is that what we got? Everybody got? So what was my numerator again? It was root something horrible.
Root 410.
Root 410. Yikes. Okay. So what is an? It's the square of this times root 410 over 3362. So somebody get out your calculator. We should get a lot of canceling here. Because the root 41, when I square it, I should get some canceling with the 3362. Now what does this end up being? I should get a lot of canceling there. Anybody got an answer? I get this. Does it come out like that? Yeah, that's a lot better, isn't it? That's, yeah. Always reduce if you can. Okay, so we got everything we need. So what is the answer? The answer is a of 2 is, where's our first number? 40 over root 41 times t of 2 plus 2 root 410 over 41 times n of 2. A lot of times, and in the textbooks, they will not even bother with the of 2's because it's kind of implied right here. You understand, it can't be of a different value than this is. But it is just good form just to remind yourself. We didn't find t of 2 or n of 2, did we? We can, but we didn't find them. We don't need to, because we already found the unit tangent and unit normal vectors. So when I go outside, hey, how big is that number? How big is that number? Let's calculate those. So 40 over root 41, that's about 6.2-ish. And 2 root 410 divided by 41 is about, ooh, it's a tiny bit less than 1. Are those numbers useful for you to understand what's happening here? So tell me about my motion. Is it fairly straight or is it pretty curvy?
4 straight.
Yeah, the straight portion is more than 6 times the curvy. So it means I'm moving, but at a really gradual arc. How do I know it's a really gradual arc? Because most of my motion is in the unit tangent direction. Very little of my motion is in the unit normal. So I'm going around a really gradual arc, but I'm not going straight. I'm definitely not going straight. Can you tell me where the center of the circle of curvature is? Yes, you can. It's in this direction right here. So whichever my normal is. So when I said there's 2 vectors governing this, but now in reality, you know, it's more like this. Right? Because way more is in this direction than this direction. So I can always describe my motion this way. Is it possible I've made an error along the way? Yeah, it's always possible. I can do a lot of different things. I know what a of 2 is. Okay? Pretty easy because a is a constant anyway, right? I know what a of 2 is. Look at those coefficients. They're kind of terrible. But if I found t of 2, icky numbers. If I found n of 2, icky numbers. If I then multiplied this into t of 2 and this into n of 2 and then added them together, I guarantee you they will add up to this. That would be the ultimate check. But that's a lot of work. Do you agree? That check was a lot of work. I don't want to do that check. No, there's a way simpler check. Remember I said there was a Pythagorean relationship between the tangential and normal components of acceleration and the actual magnitude of acceleration? Let's use those as our check. Because if those check, this can't be a wrong answer. That would be impossible. So, where's my eraser? Oh, it's over here. What is the magnitude of a of 2? Root 40? Therefore, question, does this equal that's the question, isn't it? Is the sum of these squares equal to that square? If the Pythagorean relationship is satisfied, it's impossible to have an error. You can't have that happen, but all of the numbers be wrong. You realize that's a 0 probability. That cannot happen. So with your calculator, add those two quantities together. We could have made a mistake, I don't know. Do they add up?
Yep.
Yep. All right. Cause for rejoicing. I don't want to check by multiplying the numbers through. I don't want to do that. That's too much extra work. But you notice I never actually found specifically the vectors t of 2 and n of 2. I didn't need to. Could I have found them? Sure. How hard would it be to put a 2 in there? No, it wouldn't be hard at all. But I didn't need it for the form of my answer because once I told you what the direction is, now when we go outside, you go, okay, that's the direction of the unit tangent and that's the direction of the unit normal. Right? There's no coordinate system anymore. So how much in this direction, how much in this direction, that makes it a little bit simpler. Again, we always do things, the pencil and paper, right, formal vector form, because I have a system right in front of me. I have axes right in front of me on a piece of paper. But when you go outside, you don't have axes. That's why we always have two ways to describe vectors. One with their coordinates and one with their directions and magnitudes. That's why we always describe a vector both ways. And a lot of folks don't realize those are two completely different ways to describe the same thing. Because outside, I don't want coordinates, I want direction and magnitude. And that's what this does. It gives us two different directions. Now, I mentioned last day there's actually a third vector. Oh my goodness. There is a third vector that if you're an engineer, you need to know this one also. And it turns out it's the cross product of the unit tangent and the unit normal. So let me keep it real simple. Let's suppose my unit tangent direction is along the x-axis. So literally 1, 1, 1, 0, 0. Let's suppose my unit normal is along the y-axis, 0, 1, 0. Isn't the cross product going to be the unit vector along the z-axis? And by the way, it would be a unit vector. How do I know that? Magnitude, magnitude, sine of the angle between them is still 1. That vector, I used to try to do this with my fingers and they'd always get cramped, so I'm going to do it like this now. When I'm moving through space, there is a third vector that points vertical to the plane that these guys live on. It's called the binormal. Okay, if you're an engineer, that becomes important. We don't need it in this class at all. We're never going to use it to answer anything. But there is a third vector that helps describe what's going on. And again, it's the vector that's orthogonal to the plane the other guys live on. But because the other guys are already orthogonal, this one's really easy. Because I literally get a three-dimensional coordinate system. The reason this is important, okay, we love x, y, z axes because they're easy to describe things. But it's actually because they're all mutually orthogonal. Think for a moment that if I rotated the room, and I don't mean this way, I don't mean this way, I mean have a diagonal running and rotate it along the diagonal. Now everything would be wonky, wouldn't it? There wouldn't be anything flat or straight. Well, that's essentially what you're doing. If your coordinate system is allowed to rotate and move, as long as you're keeping these three guys mutually orthogonal and unit vectors, then it doesn't matter which way you're looking at things. You always can kind of come back to the original coordinate system. How many have already had linear algebra? You've already completed linear algebra. This is the whole point of the Gram-Schmidt orthonormalization process in 3 dimensions. It creates this system to preserve things, which becomes astronomically important. It's important in chemistry. It's important in physics. It's important in a lot of situations that I maintain the orientation of unit vectors that are mutually orthogonal, even if I rotate my axes. Because when you go outside, again, right, there are no axes, so I have to have a coordinate system that's still valid. Regardless of where I am and what direction I'm looking, I still need all my axes to be mutually orthogonal, and so on. We're not going to deal with that third vector. Understand that it exists, and it will become important probably in your first upper division engineering class. Will it be hard? No, because you already know all the stuff that, that it took. So if I had asked you to do a cross product between this and this, we'd get some really ugly vector, because these guys are really ugly. But remember, we'd probably be doing it after we evaluated the vectors at numbers. So we'd be doing it with vectors of numbers, not vectors of functions. Now, I want to remind you, there's something that I see every semester that people do that makes life really difficult. They'll do all of this stuff, no more derivatives. You've done all your derivatives, and they'll do all this stuff in function form, and then at the very end of the problem, evaluate everything. Well, if you're done taking derivatives, evaluate everything and then do all your dot and cross products. It's a little easier. If you do everything as a dot or a cross product in function form, it's correct, but it can be big and ugly and nasty and full of errors. So let's look at this from a different point of view. I said there would be another way. We did all of this work last day. That's what made this fast. We would still be working on this problem, by the way, if we'd started it today. Now understand, we would still be writing because this was gnarly. Look how simple my starting vector was. Yet this was still a lot of work. So I showed you there was another way to get curvature. Anybody remember what it was? It was something divided by something. How's that? It was the magnitude of
Cross product of acceleration vector and velocity vector.
divided by
The magnitude of velocity vector cubed.
divided by the cube of the magnitude of the velocity vector. Can I use that to help me find these guys? Yeah. You're gonna like this. Let me erase this. Yeah, I got those numbers over there. We'll come back to those. So last day, we figured out that curvature, which is, let me write it out. Oops, I'm sorry. First things first. There's 2 different shortcuts we're going to do. First of all, let's do this one, which of course is, I'm going to write it in this form for a moment. This is, everything you did was correct. It's also magnitude of v. And we saw last day, and I said it didn't matter which way you did your cross product because you're finding the magnitude. Okay? That's a backdoor approach. If the algebra for finding curvature is difficult, or just really long and tedious, you can always do this route, and this route is generally simple. There's a lot of steps, but none of them are difficult. Okay? So does that mean there's a shortcut for the normal component of acceleration? Well, what is this? This is okay. Could I also write it like this? Why would I want to write it like that? Because then That's why I would want to write it like that. And what does this come out to be? That is a wicked shortcut. That's one of the shorter shortcuts. Because all I did was piggyback off what we showed last day. I can find curvature directly every time, and if it's not difficult, finding it directly is going to be faster. But if it's a problem like we just did, where some of the derivatives can get kind of difficult, I might want to backdoor. So that's the, now, by the way, let's suppose I found that and I don't have time. Can I do the other one? Sure. Absolutely, I can do the other. You know, I can do the Pythagorean to get the other one. But it turns out there's also a shortcut for the other one. It's this. Sorry, let me get rid of some of this stuff. Okay. So what if I want to do this? Let me go, I want to, just for the heck of it, let's do V of t dotted with A of t. Okay, but let's do it in its other versions that we've been using today. In other words, let's use the ds dt t dotted with d squared s dt squared t plus ds dt quantity squared k n. We know this from the last 2 days. We know this is the same as the velocity vector, right? Magnitude, speed times unit tangent. And we just derived this. Let's do the dot product and let's see what we get. You're going to like this. We get a really clean result that makes our life a little bit easier. All right? A vector dotted with itself, is that 0? No. The vector crossed with itself is the 0 vector. A vector dotted with an orthogonal vector is 0. A vector crossed with an orthogonal vector is nice. You remember that? Oh, yeah. Same direction, dot product good, cross product bad. Orthogonal, dot product bad, cross product good. I went over that last day. Because a lot of times we get those results backwards, don't we? So what is t dotted with t? Remember, dot product is distributive here. What is t dotted with t?
Just magnitude of t squared.
Which is? But I don't know what t is. T is a unit vector. What's t dotted with t? 1. You're having a unit vector dotted with itself, you're going to get 1, regardless of what direction it's pointing. Is that a good thing? That's a great thing. So when I do that first step, I'm going to get ds dt times d squared s dt squared. By the way, those can't be combined into one term. Think of one as a function, the other is the derivative of the function, times t dotted with t, which is 1, plus. Then I've got ds dt cubed times k times t dotted with n. Okay. Oh, wait a minute. What's t dotted with n? 0. Am I happy with that? I love that result. Let's go on. What if I write it like this? That is the tangential component of acceleration, right? That one thing, which in the first example I did today wasn't that hard to find. It really wasn't difficult to find. But could it have been difficult? Is it possible we have an R of t that's just a bit more busy and derivatives start getting kind of ugly and magnitudes start getting really, yeah, it's really not that hard to come up with a problem where all of this is really terrible. So I would like to know that I always have an alternate route. It's sitting right in front of me. What does this say right here? Right here, this says that V dotted with A is equal to the magnitude of V times AT. So what's AT? It's just this, which in every problem you will look at the rest of your life will be really, really easy. That will never be hard. I can't even come up with a problem where this would be hard. It's always going to be easy. V dotted with A? Oh my goodness. and we have magnitude of V probably sitting everywhere throughout the problem. Yeah, we're using that in so many places that all of these things you have right in front of you. Okay? So why don't we use those values? Let's see what we get. Now, because I want to show you the order of things. It's the same question we started with. I want you to describe A of 2 in terms of T and N. So basically T of 2 and N of 2. I want you to do this. Now we did it the long way. We did everything correctly, but it was long. And there was no part of that that was trivial. We understood it. The calculus isn't hard. It's just tedious and a lot of steps. Let's do it from a shortcut point of view. So do I want to do cross products now of all these things? No. I want to evaluate all these things. Then I want to do dot products and cross products. The tendency a lot of folks do is they'll do everything while it's still in forms of T, do all their stuff, and then evaluate at the end. I'm done taking derivatives, folks. When you're done taking derivatives, evaluate everything. It's so much easier working with vectors of scalars than it is vectors of functions. You're going to get the same answer in the end, but there'll be a lot less pain and suffering. So I don't need R of T, I need V. So what is V of 2? What is A of 2? These are the only vectors I need at this point. What is V of 2? V4 to 12. A of 2, well, it's the same as that. Okay? And what's the only other thing I need? Because it shows up in both of these? The magnitude. But not the magnitude of V. I need the magnitude of V of 2. Magnitude of V is still a square root of, functional stuff. I want the magnitude of V of 2 because that's the number I'm actually going to use in calculation. So get out your calculators. What is this? Yeah, so square root of 164, so it's 2 root 41. That 41 we've seen before, haven't we? Okay, so there's two things I still have to do. I have to do V cross A. I'll do it up here. And I have to do V dot A. All right? So let's start with V, and technically it's V of 2 cross A of 2, because if I just said V cross A, then it's implied it's still in function form. So that would be a function of T. I don't want a function of T, I want scalars. Way easier. Okay, so 12 minus 0, 24 minus 24, 0 minus 4. And let's do V of 2 dotted with A of 2, because that's the other guy we're going to need. So 8 plus 0 plus 72. Does that look right? 8 plus 0 plus 72. Okay. So in the formula, it's not the cross product, it's the magnitude of the cross product. So let's calculate that now. All right, get out your calculators. What does that come out to be?
4 root 10.
4 root 10, so it's square root of 160, so it's 4 root 10. Okay. Now, we've just done 98.3% of all the work necessary to finish this problem. This was really hard, wasn't it? Or was this really easy? Was this easier than most anything you've done this semester? Probably. Yeah. You can't mess this up because the numbers are just so nice. Doesn't matter how ugly the original problem was, this part is not going to be difficult because I'm working with vectors of scalars, not vectors of functions.
So are we ever going to have a situation where we can't use like these really easy methods, or are we always just going to be
No, but it can be that it's just still long you still have to take derivatives. And one of the areas we get in trouble is that when we're taking derivatives, sometimes we're rusty. You know, it might be of a function that you haven't worked a lot with. You know, everybody can differentiate sines and cosines and polynomials and even e to the x's, but what if it were like an inverse tan, which is still a really common function, or a logarithm? And you, oh yeah. So in other words, we can make mistakes on taking the derivatives and then all of it falls apart anyway. But will it ever be hard if you're comfortable taking derivatives? No, no. And products and quotient rules and chain rules are still all there. But when you're finding it through this route, there's a lot less of it. Because you found that you didn't do a lot of derivative techniques when you just differentiated the r and the v and the a. You had to use it when you differentiated the unit tangent, because that was already a quotient. That's where it got kind of ugly. And that's why I want you to have the backdoors, because you know how to do the calculus, and you're smart enough to know, that's going to take me a while. I know every step, but it's going to take me a while, and when it takes me a while, I might make mistakes. So I want the fast way also. So the first question people say is, why don't we just always do it this way? If I have circular motion, this is 3 times longer. If I have circular motion, I'm going to go directly, I would have been done 10 minutes earlier. No, this is not the fast way if your motion's simple. This is only the fast way if your motion's complicated. That's why you want 2 ways of going about it. You could always do it this way. You don't ever have to do the direct way. But you should be choosing the way that's fastest for the problem you have, knowing you always have alternate methods. That's better. So now, according to this, what's AN? It's this on top, and this on the bottom. Where is this? This is here. Does that look like what we had before? Yeah, because if I multiply top and bottom by root 41, what do I get? I get 2 root 410 over 41. And that's what we got before, isn't it? Oh, okay. Could I leave it like this? Yeah. Well, I'd cancel the 4 and the 2, obviously. And then what would AT be? Well, that would be the dot product over 2 root 41. Well, that doesn't look like my answer. Well, if I do this, then what does it look like? 40 root 41. Is that what it was? No, hold on. Is that right? Over 41? That doesn't feel, what was our answer before? I've erased it.
That's right.
Is this what we got before?
Yeah, we just.
Oh, we wrote it as 40 over root 41,
Yeah.
didn't we? Okay, yes. Sorry. If I just left it in that form. So did we get the same numerical values? Yeah. A lot less work? Sure. But isn't it nice now you have alternates? You have to be able to find the unit tangent and unit normal vectors. The unit normal vector is the tricky one. If I give you a simple function, finding the unit normal is easy. But finding the unit normal, the backdoors aren't going to help you find the unit normal. Unless you are lazy like me. See, I take pride in being the laziest person you'll ever meet. So if you saw my workday and you said, but I'm always working, I'm efficient. See, lazy translates to efficient. I don't want to spend an hour doing something if I can do it in 5 minutes and do it well. So how do I find the unit normal if the unit normal is always the hardest thing in the problem to find? But do we agree now that AT and AN really shouldn't be taxing? And in fact, the unit tangent vector should not be taxing. Its derivative might be taxing. But if we agree finding the velocity vector is pretty much always easy, and it really is pretty much always easy, then making it a unit vector doesn't require calculus. Just magnitude, throw your magnitudes in the denominator kind of stuff. So if capital T is not challenging to find, and I just showed you shortcuts to find AT and AN, big N is still nasty, isn't it? So you're gonna like this. See, I was a student once, a long time ago, and I had a Calc 3 instructor who wasn't particularly good at calculus. Forget Calc 3. I had an instructor, this was comical. I think the person should have retired like 20 years earlier. The person would ask questions for us and have us work on it. But then when we asked a question, like, problem number 5, I can't figure it out, and he'd go, excuse me. And he'd go over to his office, and he'd pull out the solutions manual. He'd look at it, and he'd start writing down the solution. And this was literally every single class. he'd leave class to go to his office, which wasn't terribly far away, because he didn't know how to do the problem. He'd copy down the solution. How do I know that? Because one day I got sort of tired, and so being the instigator that I was, I got up and followed him. And when I got and followed him, the rest of the class followed me, and we stood outside of his office and waited for 5 minutes. And he would turn around, he was so embarrassed. He was so embarrassed because he now knew that we knew that he had no idea what he was doing most of the time, and he was just bluffing. You know? So I had to figure a lot of things out. This was one of those things that he had no idea. He didn't even know how to find the normal vector, let alone a shortcut. All right? You're going to like this. Let's make a simple assumption. You found that. That's never going to be hard to find. Whether it's a of t or a of 2, whether it's function form or scalar form, doesn't matter. That's always easy. We now know how to find that. We now know how to find that. And that probably wasn't hard in function form or scalar form. So how the heck would I find capital N? Well, as a calculus student, I knew everything that took to find capital N, and I knew all the steps. I knew how to do them correctly. I knew it was going to take a long time. And I also knew all those other things were easy. True or false? True or false? True or false?
True.
That's how I used to do it. Because after I found the other stuff, that took about, I don't know, 3 seconds. Wait, will that work no matter what? That'll work no matter what. That'll work whether you're in function form or in scalar form. It's always true. Just use arithmetic. Well, technically it's algebra. I solved for something. Is that how you should do it? It's how you should do it if you're running out of time. But because you already know the direct path, know how to do the direct path in general, see, the problem is finding the curvature. Curvature is kind of icky and nasty. But if you found the curvature, finding the unit normal isn't that much harder because it's right there, right? You're using all the same things, magnitudes and so on. So this is a wonderful shortcut if you, like I said, if you're pressed for time. So I'm finding things, and maybe I want the unit normal vector at a particular value. I don't want it in function form. Then this is really fast because everything else is scalar form, right? This would be scalar vector of scalars, scalar vector of scalars. That would be utterly trivial for every problem there is, no matter how nasty the original problem was. You like that? You should. That's not going to be in any textbook or on any YouTube video or anything. I don't know why. To me, that's just such a no-brainer. It's like, really? It's really that easy? Yeah, but it's because you found all the other stuff. That's the key. You can't do that if you don't have all the other stuff. It won't help you. But if the other stuff is less challenging, you can always do this. And remember, your goal is to describe motion. You want to have your numbers right, and you want to know that your numbers are right. This will only work if all the other numbers are right. So remember, how do you know if your numbers are right? Well, I said one of the ways was to check the coefficients by using a Pythagorean relation. Don't use the Pythagorean relation necessarily to find the missing one. You can. Remember, if you have an error, then all the numbers would be incorrect. That's the one danger. That's the one danger. A lot of times we do shortcuts. In linear algebra, I mean, today I'm going to show shortcuts. We do a lot of shortcuts that are wonderful that rely on a previous answer. But the shortcuts are only valid if the first answer was correct. And a lot of times, and I'll show people the shortcuts, they'll apply them, but the first answer was incorrect, which means everything they wrote is incorrect. So the problem with some of the shortcuts is there's no check. Does anybody follow? So that's why the Pythagorean relationship is one of the best checks, because again, if it checks, you can't have wrong information. So let's do a problem, another problem, but from start to finish. Now that we know all the pieces, and we can decide as we go, when I'm writing answer keys, I will sometimes do it one way, and the next time I do it, I'll do it the other way, just to show you versions of the truth that you can do it either way. And you know that if you did it right, the answer will be correct, even if you take an alternate path. That's the one thing you can always assume. Now, I want to remind you, today we are finishing everything related to the exam, so I will be posting the practice tests later on today. And if you've been in my class before, you expect this. There's a practice test and a key that's very, very reflective. And how many have been in Calc 1 or 2 with me before? In this group, nobody's been in Calc? Does the practice test look like the test? Yeah, basically. And what's I always find amazing, even in a calculus class, is how many people will show up to a calculus test never having looked at the practice test. Like, really? I just gave you the test and the answers to the test and you didn't want to look at them? No, it's, and by the way, every quiz question I've asked you, I already did that problem in class in tremendous detail with explanation. So you probably want to get it right. I say that jokingly because on the last quiz, I saw some methods of finding surfaces that I haven't seen in a long time. That, by the way, they're methods that don't actually exist. But people are doing all sorts of interesting things that I've been doing this for a long time. Some of you really, it was awesome. I rarely see errors that I haven't seen 1,000 times. And I saw some errors I hadn't actually seen before. You should feel proud. I came up with an error that no one's ever come up with. But the thing is, finding a surface, there's never going to be anything you do the rest of your life that will be as easy as identifying a surface. So you can't get it wrong. And about half of all the answers were wrong. They weren't even ballpark. I have no idea what people were doing. Right? Finding a cross-section, there's no math. You just say, here's my cross-section, it's a parabola, it's an ellipse, it's a circle, it's a hyperbola, now I named the object. I gave you notes, we did it in class. I have a 5-minute video, I have a Zoom lecture, I have a class video. I've done it so many times and I did the same problems over and over again. That's when you want to get right. It's too darn easy. I mean, should you be embarrassed if you missed it? No, but you should ask yourself, how did I miss this? This was the easiest thing going. And I mean, people use techniques that don't exist. You'd be amazed at how many people said, well, I'll just evaluate everything at 0, and all the answers were, there's no shape, there's no shape, there's no shape, it's an elliptical hyperbola. You know, all the cross sections were no shape. That's not a possible answer, by the way. I don't have a shape. Or, all of my things are only imaginary coordinates, therefore my answer is. You can't have imaginary coordinates. That's not a good answer. Yeah, that one you want to go back over. It's not a major deal in this course. I'm never going to ask you to identify a surface again. So why do we do it? Because starting next day when we start doing functions with 3 variables, you actually have to look at a problem and know what it is immediately. I'm never going to ask you to write it out. Every single shape you look at, you actually have to be able to look at it, see all 3 cross sections in your head, and then know what it is. That's not memorization. Because there's an infinite number of variations. You can't memorize even one of them. What you have to be able to do is say, oh, okay, x, y, x, z, y, z, they're this, so this is what the shape is. Therefore, that shape is going to have an absolute maximum or an absolute minimum or a saddle point. That's what you're going to be doing next. That's why you have to be able to identify them when it's easy, because you're going to now use them to answer questions later. I'm never going to ask you what they are later. You just have to know that's what it is, because you won't be able to answer the higher level question. That's the point. So that's one, it's easy enough, we want to get it right. So let's look at a problem, let's see, where the numbers are, I did this is on the notes, the numbers are not quite horrible, but also not very nice. This is similar to one you just did recently, right? I think this is similar to an arc length question I just asked you. Okay, if we wanted to do anything with this, that's not terrible because none of my derivatives are difficult and each term is only one term. So I can work with this. You see the fractional exponent, you get a little, maybe a little nervous, but regardless of the coefficients, the path I take, I want everybody to do the same thing at the same place. And what I want to do in this problem is I want to attack it literally from every point of view so that you can decide on your own what is the most optimal path for me. There is no such thing as a one-size-fits-all. And funny thing is, on the quiz on this stuff, half the people will go one direction, half the people will go the other direction, and they'll all be correct. And I mean in terms of which technique you want to use to find the pieces. Because when you're looking at the problem, you go, one doesn't really seem to give me an advantage over the other, so I'm gonna go to the one that I think I might be better at, and that's still the right decision. If you're right, but you don't wanna take the harder path. Always take the path of least resistance when you're doing problems, and you can only know that through repetition. You say, oh, okay, I've done problems like this before. So let's do the derivatives first. So what do I get here?
24t to the 1/2. 12t.
12t and
24.
this guy,
12t to the negative 1/2. 12 and 0.
am I concerned about the negative half? No, because I'm going to be evaluating these at numbers soon enough, and then I can deal with that. It's absolutely correct. If you'd rather write it like this, that's fine. It doesn't make any difference in the long run. Okay? Now, I do this as just a force of habit. I do all three things before I even start anything else. I may do the direct route, and if I do the direct route, then I'm really probably never even going to refer to this one. But if I do the indirect route, am I going to refer to this one? Yes, I got to do A cross V, and I got to do A dotted with V. So that's why I'm going to do that. Now let's find the other pieces. What is the magnitude of the velocity? So sum of the squares, so what's that? 576t plus 144t squared plus 576. I like that. Now, a lot of you, this is where you lack the lazy bone. You're looking at these really big numbers that all three are multiples of 144. Since all three are multiples of 144, that's a little easier to do it like that, isn't it? And that's just t plus 2 quantity squared. Does this look vaguely familiar? Yeah, you just had a quiz that looked like this, where it ended up, how did I do that? Yeah, I reverse engineered the numbers, so it turned out to be a perfect square. Is that always the case? If I change any number or any exponent, will that be clean and simple? No, it'll be hideous. It'll be hideous. Does it mean you can't do it? No, it just means you won't be able to simplify it nicely. You just have to leave it as a big, icky, ugly square root. That's not wrong. That's the majority of the problems. It's just this one came out kind of nice. So after all that, it's just 12 times t plus 2. Factored or not factored, that's not too bad, is it? Okay, so now let's look at the tangent vector. So what I'm going to do is throw that into the denominator of all those guys, and since those are all multiples of 12, that makes it a lot easier, doesn't it? So I'm going to get t to the 1/2, actually 2t to the 1/2 over t plus 2. I'm going to get t over t plus 2, and I'm going to get 2 over t plus 2. Does that look correct? I think I did it right. Is it possible that that's not correct? Well, why don't we check to see if it's a unit vector? How do I check? Sum of the squares. So let's square the numbers on top. And what do we get? We get 4t plus t squared plus 4, which is t plus 2 quantity squared. And my denominator was t plus 2. By the way, at first glance, what I would be suspicious of, because I have 2's on top. How could that be a unit vector? Well, because it ended up, yeah. Still do the check just in case. So there's my unit tangent. Are derivatives of this going to be evil and horrible, or are they going to be probably, okay, not the worst thing I've ever seen? I don't have any roots in the denominator, so the derivatives won't be the worst thing I've ever seen. Okay? But you've decided, I don't really want to take any more derivatives. I want to kind of leave it as is. You could do that. I believe I want you to do this at, we're going to use it t equal 1. Okay? So we're going to find ultimately a of 1 in terms of our stuff. So let's take the backdoor method at this point. Okay? That means that I can now evaluate these guys at 1. I don't want to do the cross product in this form. I can. But if I do the cross product in this form and then I carry all the way through, then I'm going to evaluate that at 1. It's extra work. Remember, you're going to do the cross product, then you're going to take the magnitude of the cross product. You realize how big the magnitude of the cross product is going to be when you have it in function form? It's huge. You have a huge thing under a square root, and then you're going to do all this stuff and then evaluate that. That's what a lot of folks do. Don't. Evaluate it, then take the cross product. You don't have any more derivatives to take if you're going to now attack the backdoor methods. If I want to find it directly, I still have to take a derivative, don't I? And we're going to do that also. But I want to do the backdoor first just to show you how simple and clean it will be at this point of the game. So, I need v of 1. What's v of 1?
24, 12, 24.
I need the magnitude of v of 1. That's really easy, isn't it? What's the magnitude of v of 1?
36.
36. And I need a of 1. 12, 12, 0. Okay. So, A of 1 cross V of 1. If I write A cross V, it's kind of implied that it's A of T. When I drop the of T, when I write capital T, it's implied that it's of T, right? Capital N of T. We can get lazy and do that. But if I'm evaluating a particular number, I really need to show that, because otherwise, that would still be in functional form. So what is this? So 0 minus, or if it helps you, you can be really lazy like this. So 0 minus 288. And 288 minus 0. And then 288 minus 144. Oh, those are big numbers. And I need the magnitude of this guy. Oh my gosh, that's going to be so big. Oh, and I don't have my calculator with me. Darn. Do we have any lazy folk here? I'm hoping. Just so you know, this is what I do always. I don't ever work with the given numbers unless they're all prime or something. What's the magnitude? 144 times the square root of 4 plus 4 plus 1, which is 3. So your magnitude is 432. Did you need a calculator? Not if you recognize all your numbers are multiples of 144. Is your magnitude usually an integer? Or is it usually a root? It's usually a root. So the problem with the magnitude of a root is if I have a big gargantuan root, I don't know if it reduces nicely, unless I have that calculator that reduces roots. That's a good calculator to have, but not everybody has that calculator. And a lot of us just don't have the patience to go by hand. So if I had done this squared plus this squared plus this squared, would you say those numbers are ginormous? How big are those numbers? Well, they would have added to 186,624. And you all know that number off the top of your head being 432 squared, right? Everybody knows that. You learned that as, first grader probably. Or would you be spending 10 minutes trying to whittle it? Okay, divided by 4, divided by 4, divided by 4. That's what we learned to do. No, don't do that. Make it easier on yourself. Okay, this is one of the numbers I need in the answer. So now what is A of 1 dotted with B of 1? And by the way, it doesn't matter what order I wrote it in. I'm purposely writing it backwards because it doesn't matter. It's dot product. So I am taking these two vectors. So I have 24 times 12, that's 288, plus 12 times 12, that's 144, plus 0. Oh. Okay, that's coincidence. We could do 1,000 problems and never see those two numbers being the same again. oh man, I just figured out a shortcut in calculus. Dot product and magnitude of cross products will always give me the same value. Right? Or they didn't on the last problem, did they? No, like I said, I could do 1,000 problems, it's never going to happen again. It's just sheer luck. All right, what is AT? AT is this over what? Over this. And what is that? 12. AN is this over this. Oh. Oh. This is kind of an interesting problem. You don't see this very often. My tangential and normal components are the same. What do you think a motion looks like?
Going out of 45.
It's not a circle, it's not a line. It's a pretty good curve. I mean, 12 is fairly large coefficient in this case, but I have just as much straight as I do curve. I don't know that I could describe exactly what that looks like. It doesn't look like a circle, but it's definitely not a line. It's kind of, I mean, if I drew a circle and I drew a line and I sort of, I like what you said, kind of go maybe off at 45, sort of mentally, you know. So what am I doing? I'm probably kind of going off, you know, sort of an in-between direction, I guess. But it's curving. You're just saying you have the same in each direction. Great. So now I wanted to write, in terms of the unit tangent, unit normal, I wanted to describe A of 1. It is 12 t of 1 plus 12 n of 1. That's what it is. Now, in reality, okay, I want you to go outside and I want you to go exactly 12 times the tangent vector and 12 times the normal vector. You're going great. And which way is the normal and the tangent pointing? So don't I kind of need those vectors? I told you the coefficients, but if I don't tell you, you can't go outside and just make up two directions, can you? You know the coefficients, but don't you kind of need the t of 1 and the n of 1? Oh, yeah, I kind of need those. Well, do we have t of 1 sitting right in front of us? More or less? What's t of 1? You like this? It's 1/3. Is that right? No, I'm sorry, not 1/3. Sorry. It's 2/3. Sorry, 2/3, 1/3, 2/3. Huh. 2/3 squared plus 1/3 squared plus 2/3 squared is 1, in fact. Can we find the normal vector? I really would like n of 1. We have two ways we can do it. Let's find the derivative of this, find the magnitude of the derivative of this, and then make the derivative of this into a unit vector. That's how it's always done. That's not the worst thing in the world, but I do have some quotient rule, and I got some stuff going on there, and it's not the worst thing in the world, but it might take me a couple minutes. I said there's another way. Do you remember what it was? What is it? Well, why don't I take A of 1, what's A of 1? 12, 12, 0. And then I want to subtract 12 times t of 1. And then what do I want to do with all of that? Multiply it by 112. Remember I just showed you a shortcut working backwards? That's what I'm doing right here. Let's figure out what it is. Did I lose one?
This time should be 1, right?
Oh, I'm sorry. Is that what I'm too far away? Is it 1?
Yeah.
Thank you. Yeah, this should be a 1. Sorry. I just can't see that far away. So this, what is this right here? What is this vector right here? This is a of 1 minus at times t of 1. And then this is 1 over an. I don't need you to memorize that, but do write that down because you're going to find this is kind of a nice little shortcut. So when I do this, well, let's see, what will this be? This will be 12, 12, 0 plus negative 8, negative 4, negative 8, which is now 4, 8, negative 8, all times the 12. So what is my normal vector? It is 1/3, 2/3, negative 2/3. Is this a unit vector? Check that first. Is it a unit vector? Square, square, square. Does that add to 1? And more importantly, is it orthogonal to t of 1? 2/3 times 1/3 plus 1/3 times 2/3 minus 2/3 times 2/3. That is equal to 0. Now, this is the normal vector evaluated at 1. Boy, that wasn't too hard to find, was it? What are we relying on? Absolutely relying on. All the pieces of the puzzle were correct. Is it possible that there was an error along the way? Is it possible? Yeah, and I mean something as trivial as when I took this derivative, I got the wrong coefficient. It is possible there's an error along the way. And what would that mean about that answer? It means every single number in that answer would be completely incorrect. So this is the chance you take, okay? By doing what I just did, that was a tremendous shortcut. But I'm taking a chance saying everything has to be correct. Now, you say, but it all worked out in the end, but I did a vector that was orthogonal to another vector that might have been the wrong vector to begin with. Oh, aren't I basing this on my t? Yeah, so let's also calculate in the old-fashioned way. By the way, we never actually found curvature, did we? We never actually found curvature. Because in this problem, you weren't asked for curvature. On the exam, what I often do is, if I have a problem where I ask you every single thing, AN, AT, curvature, T, but that means it's probably not hard to find. Maybe it's circular motion or something. And I'll have a problem where I only ask you for curvature because all of the pieces can take a really long time. Or I have a problem where I only ask you to put it in this form so you could use the backdoors for AN and AT without actually finding curvature directly. Sort of every version of a question, but not all questions at the same time, because that can make it really, really long. So this is basically the next quiz. So what I want to do is actually find n of t, because sometimes that's the question I ask you. I say, what's n of t? Well, this stuff isn't particularly useful if I'm trying to find n of t. I actually have to differentiate this guy. So let's start with, what is dt dt? So off to the side, now I said lastly, there's a simple rule of thumb when it comes to quotients. If your denominator is something raised to a power, always write it as a product. My denominator is not something raised to a power, so writing it as a product to the negative first power isn't advantageous. It actually is longer. No, it's easier just, this is one of the kind, it doesn't go straight up quotient rule. There's no advantage to rearranging this one. What if my denominator had been t plus 2 raised to a power? Whether it be a square root or whether it be a square, then I would have written it as a product. That would have absolutely been an easier problem to do. But there's no advantage because I just have just a simple thing. So bottom times derivative of the top, which would be, what, t to the negative half. Stuff. Minus the top times the derivative of the bottom, which is just 1 over the bottom squared. Oops, that's a 2. All right, well, may or may not be nice. So what's my numerator? It's t to the 1/2 plus 2t to the negative 1/2 minus 2t to the 1/2. Does this come out nice? I don't think so. So what does this end up being? 2t to the negative 1/2 minus t to the 1/2. Whoops, sorry, I lost my denominator. Let me do this again. That's t plus 2 squared. So this is on top. Oh, if I put those guys first, I can write this. Negative t to the 1/2 plus 2t to the negative 1/2 all over t plus 2 squared. Don't really like that a whole lot. How do I make that cleaner? Because I can't have that negative exponent on the top. What's the easiest way to do this? Just multiply top and bottom by t to the 1/2. And when I do that, what do I get? I get negative t plus 2 over t to the 1/2 t plus 2 quantity squared. That's a big yikes. That's the first one. By the way, that's the only one that's going to be terrible. So I have, and by the way, we're going to find n of 2 in the end. So this really won't be a problem, but if I try to evaluate, or I'm sorry, n of 1. N of 1 at the end, so if I evaluate this, it wouldn't be the worst thing, would it? Because it'd be 1 to the negative 1/2, but when I evaluate this at 1, that's not going to be terrible. Okay, that derivative looks terrible though. And then the top was, you know what I'm going to do? Because we know we're going to evaluate this at 1 eventually, I'm going to leave it in the ugly form. And I'm going to show you why. I'm going to leave it in the ugly form there, where I have halves on top. So it was negative t to the 1/2 plus 2t to the negative 1/2. And the reason I'm going to leave it in the ugly form is the next two derivatives will have a t plus 2 quantity squared in their denominators. But they won't have the t to the 1/2. And remember before, we kind of need our denominators to be the same. As awful as it makes our numerator, it's more important that the denominators are the same. That's what personally, that's what I think. Okay, so the next one is what? T over t plus 2. Well, that should be easy. So the derivative of, what's the derivative of t over t plus 2? Okay, so bottom times derivative of top plus top times, or sorry, minus top times derivative of bottom. Did we do that? Okay. And then bottom squared. What does that give us? Well, the t's cancel, and I just get what?
2 over t plus 2 squared.
Is that all I get? Oh, okay, that makes sense. So that's 2 over t plus 2 quantity squared, and then the last one, of course, will be negative 2 over t plus 2 quantity squared. Think of that as t plus 2 to the negative first, if it helps. All right, this is not a unit vector. So I need to find its magnitude. Yikes. So I got to do the sum of the squares, but everything's got a t plus 2 quantity squared. This is correct. Could I do this? Is this true? Why would I do that? Because when I find the magnitude, that's already there. Most of us will do all this stuff, we'll square stuff, take the square root, and in the end we still have this in the denominator. So all I really need to do is find the magnitude of this, and then put it over this. Because that's what we would have got anyway. Does that make sense? So let's do that. Again, being lazy sometimes makes life so much easier. All right, so when I square those guys, I'm going to have negative t to the 1/2 plus 2t to the negative 1/2 quantity squared plus 4 plus 4. Right, sums of the squares. So this will be t minus 4 times 1 plus 4t to the negative first plus 4 plus 4. So now I have t plus 4 over t plus 4. That's correct. I don't see anything yet. What if I make that into one quotient? Then what will I have? T squared plus 4t plus 4 all over t. Huh. Why would I do such a crazy thing? Because this is under a square root, isn't it? And won't that be t plus 2 quantity squared over t? Oh, I like that. So therefore, when I do the square root of this, what do I get? Just the t plus 2 over a root t. So the magnitude, sorry, I'm running out of room here. Where am I going to put this? I'll put it over here. So the magnitude of dt is t plus 2 over the square root of t over t plus 2 quantity squared. Remember, that was my numerator. Well, that leaves me only then 1 over root t plus 2. I can cancel one of those t plus 2s. That was a lot of work. That's the magnitude. By the way, I need this for curvature. So now what am I going to do? I'm going to take the reciprocal of that and multiply it by this, and obviously a t plus 2 will cancel, won't it? One of the t plus 2s, not both of them. So, when all is said and done, and there's nothing left to say or do, what is n of t? The reciprocal of this, so one of my t plus 2s will cancel. Leave the one on the outside just to make it easier for now. When I multiply by this on top, I'm going to get root t over t plus 2, aren't I? Times negative t to the 1/2 plus 2t to the negative 1/2 to negative 2. Okay, can you all see that? Now when I distribute, this isn't, no, it's not going to be pretty, but it's not going to be as terrible as you think. Again, I took the reciprocal of this times this. And now that is my normal vector. So now when I distribute, root t times, that's going to be negative t plus 2 over t plus 2. This will be 2 root t over t plus 2. This will be negative 2 root t over t plus 2. If I take the sums of the squares, hopefully I get a unit vector if I did it all right. I'm a big fan of checking. So let me take the square of that. That'd be t squared minus 4t plus 4. The square of that plus 4t. The square of that plus 4t. That's t squared plus 4t plus 4, which is t plus 2 quantity squared. Or is it more of a? Sometimes, do we rejoice or do we just sigh of relief that we didn't mess it up? I've just proved that is a unit vector still. I don't want to do a dot product with this, because our goal is to find n of 1. This is n of t. I'm going to check my dot product by finding n of 1. It's easier. What is n of 1 now, after all is said and done? Sorry, let me put this up higher. I'll put it up here. I hate doing this to you, but I'll put it right next to the t now. So, after all of that work, because I wanted to find n of t, what is n of 1? Let's put the numbers in. N of, all my denominators are going to be a 3. So n of 1 would be, what? 1/3, 2/3, negative 2/3. Is that the result we got the first time? When we did it the backdoor way? I think it is. How can I be sure? 2/3 plus 2/3 minus 4/3 is in fact 0. So we did it right. This wasn't the worst problem in the world, but this still took us a really long time. That's why you need to have a backdoor method. You are really good and you're a great proofreader and you just don't make careless errors. Can you trust that you didn't make a mistake along the way sometimes? Can you actually do that in real life? Yeah. It's always good to have ways of checking. But if you know you're careful along the way, you're pretty good, and you just don't seem to make a lot of careless errors, absolutely you can take shortcuts by using previous results to get the next result. But I said the danger is if you have no way of checking along the way, you could have an error from the beginning, and then everything was messed up. Believe it or not, people will do everything perfect, but they wrote the problem down wrong maybe. So something silly at the beginning, they do all of this work and it ends up being, it's a completely different problem. And I'm checking my work going, nothing's working. Why is, I looked in the back of the book and everything's different because I wrote it down incorrectly. I perfectly did a different problem kind of thing. So we've looked at this problem from every conceivable point of view and now we know how to do all the pieces. So have all of your methods written down next to each other. Have both ways. AT, little a of t, is the second derivative, right, of arc length, of s. So it's d squared s dt squared. That's what it is. But it's also equal to v dot a over the magnitude of v. We proved that. They're always equal. So whichever one is easier at that time, you find. And sometimes doing the derivative of a ds dt can be easy. Most of the time, it actually is easy. But then the other way can be a check that I did it right. Then curvature, curvature's not always easy. But now knowing it's the magnitude of the cross product over the cube of the speed is an easy way to check it. So I did it the long way and I checked it using the other. That's also a thing you can do. The only time in life you're ever truly timed is when you're taking an exam. Your work wants you to do something. You have a work project and they need it on Monday. Are you being timed? No. You don't even have to start it till the weekend. But they need it by Monday. So you've got all the time in the world. You want to be right. So what you want to do is do it directly, check it with the backdoors, perhaps. Because again, how do you know if you're right? But the backdoor was a completely alternate way of getting to the same final answer. And when I do it and I check it with the backdoor and I get the same result, it would not be possible that it's wrong. Because I found them independent of each other. That's the key. So little things like that. On an exam, you usually don't have time to do both. So that's why I say on an exam, you go toward the one that you feel faster at. It's just safer. Okay? Because exams, you're being timed. Nowhere else in life are you truly being timed. But at work, you say, I'm not being timed, but if I'm wrong, I'll get fired. So I want to be right. And again, you have options. You know there are other ways. Okay? Let's go ahead and stop recording. Hit that.